Today we will talk about inductors. Inductors are passive elements that operate under the principle of magnetic fields. So we will learn about inductors and of course about magnetism and magnetic fields. The agenda or the outline or the objectives are to become familiar with the basic construction of an inductor, the factors that affect the strength of the magnetic field, how to read the values of the inductors, how to be able to determine the transient or time variant. Transient means time variant response of an inductive network. So let's talk about the magnetic field concept, which is applicable to inductors and to electromagnetic um, waves and to a lot of sensing equipment, and obviously it's a very important concept. Magnetic fields are important concept for sensing and for operation of machinery and for electromechanical applications. So first of all, magnetism is a property of certain metals or certain materials, mostly metal or transition metals, and magnetic fields operate in a way where there's a polarization. So if you have a magnet, you can compute or you can determine the field strength, the magnitude of the strength by putting another metal that is magnetic around or by focusing in a certain area where the magnet is operating on. So this is a good example. If you have a magnet and you place a piece of glass or a piece of plastic nearby, the lines of magnetic field will go through it without affecting the glass, or better yet, the glass does not affect the magnetic field. However, if you put another magnetic material nearby, the magnetic field is going to be disturbed by this metal or by this material that has magnetic properties. And that is very interesting because we can build applications around magnetic fields. So for instance, we have a generator, and this is a good application for generating electricity or for obtaining three-phase electricity. So, or even one-phase electricity. So like the electricity that you get at your house could be made by a generator at a power plant, where this is rotating at certain frequency and is generating the frequency of the positive and negative voltages that we need. And of course, transformers have the concept of magnetism built within them, where it's basically using magnetic flux density to be able to carry the um, electric current, and to be able to step down the voltage. Speakers use magnetic fields, so we basically have a signal, electric current, and the magnetic field form use can be translated from the electric current to the magnetic field to polarize a different material. We have sensors with magnetic fields. Relays also have magnetic fields. So, and we'll see that whenever you have electric current, you can compute magnetic properties in a conducting element. But medical applications also use magnetic fields. So magnetic resonance, so MRI, for instance, is based on magnetic fields. So when we talk about a conductor and we place electric current through it, so let's say electrons are flowing through this conductor, by the flow of electrons, we have a magnetic field around the conductor. And as you know, or you will learn at some point, if you have an electric, if you have voltage or electric field traveling through space, there's a magnetic field flowing perpendicular to it. So electromagnetic waves show us that electric and magnetic fields are connected. Hence, if you have electric field or if you have electric current flowing through a conductor, you can measure the magnetic field around it. Okay, sometimes that could be very weak depending on the material. Sometimes it could be very strong to the point that we can use that magnetic field for sensing or for other applications. So the interesting thing is that by having a geometrical factor or by playing with the geometry, you can have different magnetic fields. So they can build on top of each other, they can get stronger, they can get more dense, etc. So inductors, for instance, use a coil of conductive material to be able to increase the strength of the magnetic field. So the inductor is constructed based on the principle of electric current flowing generating a magnetic field. So if you have, as we mentioned before, in fact, before anything, I want to mention that the diagram from an inductor is this little coil figure showing that the current goes through it and there's a voltage potential across it. If you want to determine the voltage across it, you simply have to derive the current with respect to time and multiply by the inductive constant. So we have different geometries also for the type of inductors that we want, and they could have different properties based on the materials that we use as the base conductor where we wrap the coil around for the current to be able to flow. So if you want to compute the current based on voltage, you can just integrate your voltage functions. Okay, power can also be computed, and it's basically the derivative of it, current with respect to time, times the current, and times the inductive constant. The stored energy in the element can also be computed based on the half of the inductive constant times the current squared. So, for example, consider a switch that closes at time equals 0, so at initial time, connecting a 10-volt source to a 2 Henry's inductance. Henry's are the units of inductance. Find the current as a function of time. So it's telling us that at time 0, this is open, then when it closes, we want to find the current as a function of time. Okay, so the figure for voltage is pretty simple because it's a DC source. So it's going to be 0 while the switch is open, and it's going to be 10 volts as long as the switch is closed. Okay, they gave us that the current has a function 5 times t. So this is the rise. Basically, in 1 second goes up to 5 amps. And they want us to find the current as a function of time. So we just have to integrate, and you can use your calculator, or you can use Python for this, or you can just use your calculus if you want to find the current based on the function. And this function is determined experimentally because you can use sensors and oscilloscope and multimeters to see the time that it takes to go to the highest amperage that the circuit is rated for. And if you see that it takes, okay, 1 second, it goes to 5 amps, then this function is 5t. So don't think that this is not applicable in real life, because it is. And the voltage is simply the integral of, I'm sorry, the current is the voltage integrated over the time period. And if you do that, you will find that we can basically find the functions at different time steps. So for example, they give us a DC circuit that says that initial time 0, the switch is closed, and then we're connected to a 10-volt source or a battery. with a 2 Henry's inductance. The coil has, this inductor has units of Henry's. Inductance has units of Henry's, and the value is 2 Henry's for this particular inductor. They're asking us find the current as a function of time. So the answer is 5t, but how do you get to this answer? So first of all, this could be a real world application where if you measure with the oscilloscope or with your multimeter, you can see that when you close your switch, the voltage goes up to your maximum source, the voltage of your source. But then you can measure with the oscilloscope the time that it takes for the current to reach its maximum values. Okay, so the other way is by doing it mathematically, which is pretty simple. We want to find what is the current, the function that determines the current. In case we change the inductor or in case we change the times, we have a function so that we don't have to build every circuit every time. So that's one reason why mathematics are so useful dealing with these type of problems. So when we have want to find the current, we know that we have to integrate the voltage, and the voltage for a DC circuit is very simple. It's just a uniform constant, it's a constant. It's 10 volts. So this is going to be 10 dt, which is right here, and the inductance is 2. So 1/2. This is going to be 2, and this is 10 dt plus the current at time 0. This is going to be 0 because it's originally open, and we don't have any capacitors, so there's no current at first. And then when you integrate this, it should be pretty simple. This will be 1/2 times 10 t evaluated from 0 to the t that we want to do, 1 second or 3,000 seconds, whatever it is. So this is going to be canceled out, and it's going to be 5t. So the function is right here, 5t, and this is the function that we should get. If we were to build this circuit and measure experimentally, we should be able to get this slope with an oscilloscope. Now, if you want to find the voltage, is even simpler because voltage equals L di dt. So you simply have to derive that again. So let's see. Voltage is L di dt, correct? So that's what we need to do. And we know that, let's say, they're just saying in 2 seconds. So the first thing we need to do is evaluate this function in, say, the IDT equals 5. So V equals L times, or 2 times 5. The derivative of 5t with respect to t is 5, so it equals 10. Okay. I think that this is not, if we say 10 milliseconds, this is not correct. So I think I got this from a different example when I was building this example right here. So this is not true because A, these units are milliseconds and these units are in seconds. And 2, because the question is find the current, and we just did. So this is probably a different example. I'm gonna check that. So when we have inductors in series, we can just pretty much like resistors. Remember resistors, you can find a total inductance, or LT or TL, total inductance, by adding up the independent inductances. When they're in parallel, they also behave like resistors. If you remember from your DC class, you have to do the equivalent, or the total inductance is 1 over 1 L1 plus 1 L2 plus 1 L3, just like this. So this is pretty simple stuff. You just have to be careful though with the units. The only place I see you can get errors is if you're not equipped with the units. If this is micro and then there's nano, Henrys, etc. Another interesting application for magnetic fields and the concept of inductors is for a linear variable differential transformer. So transformers, as we saw, use the inductance of conductive materials to be able to increase or decrease the voltage and the current throughout the system. If you want to find the new voltage, you simply follow this set of formulas where V1 is L1 times the change in current with respect to time. So if you have a function for this, is great. If not, you can measure experimentally independently each circuit if you're in the business of making transformers. And also m times d2 dt, di2 over dt. So my m is going to be the force in this region. If you want to find the step down or step up voltage, you follow your system of equations and you can find those. And in fact, people or companies do these computations beforehand to know how many loops they have to create, what is the type of current that they need, etc. So we come to a concept that is the magnetic flux and flux density. First of all, the flux density has units of Tesla, and the magnetic flux has units of Weber. So the flux density is the magnetic flux through an area. So remember, when you have a magnetic material, let's say this is the north part, this is the south part, and then it's going to be flowing like this. If you take an area, a plane, and you measure that area, and you see how many lines are going through it, how many magnetic flux lines are going through it, you can find your flux density like so. This is your flux density B equals your magnetic flux divided by your area. Okay. So another interesting thing is magnetic force, is the magnetomotive force. So the magnetomotive force has units of amperes per turn, and or short is AT, and is basically the number of turns in a coil times its current. For instance, if you have a conductive material and you want to increase the strength of the magnetomotive force, you have two options. Either you increase the current or you increase the number of turns. Of course, the number of turns, you have the restriction of the geometrical restriction of the length that you have available. If you increase the current, you could run into burning your circuit. So that's why you have to have things that are proportional in current and in number of turns, and the thickness of the wire, etc. So it really depends on the application. The inductance is computed based on the magnetic permeability. The magnetic permeability mu has units of Webers over amp meters, and the number of turns in a coil, obviously the area, the length, this length right here, and that will give you your inductance. Okay, this is measured experimentally and is pretty much like the dielectric property, the dielectric constant for capacitors. The permeability is a magnetic property that each material has, and you can measure it experimentally. The permeability of free space, which is mu sub 0, is 4 times pi times 10 to the negative 7 Webers over meter. For inductors that are circular or cylindrical, the length is the perimeter. The number of turns are still the same. You just count the number of turns, and the area is the thickness of the loop of coil. So obviously you have different applications, different sizes, different number of coils, and that's again depending on how much inductance you need and how much current you need. If you notice, this wire is way thicker than this. It's thicker than this, therefore you can have more current going through this one. Also, there are tiny inductors, and they are usually for small inductances. So for DC applications that are very small, for milliwatts power ranges, you can use very tiny inductors.